Introduction to sine graphs. Today we're going to talk about taking our sine values off of a circle, and now we're going to stretch them out across an x-axis. So we're going to have a better pictorial of what we talked about earlier in the week when we talked about sine and cosine's domain and range. And you're also going to better be able to see what's called a sinusoidal pattern. So everybody needs to have a unit circle graph handy. Today we're going to focus just on the sine functions. Today we're going to focus just on the sine values. Those are your y values. Okay? So we talked about earlier in the week the periodicness. In fact, Wednesday was when we talked about it, how these graphs are periodic. So here sine we talked about being periodic every 2 pi. So if I took a point on the circle, say pi over 4, and I found pi over 4 sine, the square root of 2 over 2, 1 pi later, it's the opposite sign. It's not until we get to 2 pi later, one full rotation, that it repeats itself. Okay? So we're going to look at how that looks today when we talk about one full rotation being 2 pi. So here, when we consider the period for sine as 2 pi, what we're going to do is to get our quote-unquote x values, which are really our sigma values, we're going to take that period and we're going to divide it by 4. So 2 pi divided by 4 reduces to pi over 2. So we're going to talk about pi over 2 increments. So we have 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and then we wrap back around to 2 pi. So one of the new things that we're going to be talking about here is the amplitude of the graph. And the amplitude of the graph is how, quote-unquote, tall the graph is. So let's take and use our unit circle to fill out the rest of the table. So at 0 degrees, looking at our unit circle, at 0 degrees, what is the sine of theta? I'm sorry, 0 radians. 0 radians has the sine of 0. Remember, this is your y values. At pi over 2, what's the sine of theta? 1. At pi, what's the sine of theta? 0. At 3 pi over 2, what's the sine of theta? -1. At 2 pi, what's the sine of theta? 0. In fact, if you keep going around and around and around the circle, you're going to see that every pi over 2, this repeats. So we hit back up here at 0. Well, the next quarter rotation is 1. The next quarter rotation is 0. The next quarter rotation is -1. Next quarter rotation is 0. Next quarter rotation is 1. This pattern extends infinitely because our thetas, we can go around that circle an infinite number of times. So we have an infinite number of possible values for theta. So that's why earlier in the week I told you that the domain was all real numbers. So now let's look at the graph of this and see what it looks like. So we have 0, 0. Now this is our theta axis on the x-axis, and this is our sine of theta axis here on the y-axis. So at theta is 0, the sine of theta is 0. At a theta of pi over 2, the sine is 1. At a theta of pi, the sine is 0. At a theta of 3 pi over 2, the sine is -1. Keep that scale consistent. And then at 2 pi, we wrap back around to 0. So here we see this sinusoidal pattern, this wave that goes up and down. And if we were to continue this, again, it would be 1, 0, -1, 0, 1, 0, so on and so forth. And this wave that we've created would just keep on going infinitely. Now, what about the other direction? take a look at your unit circle. If we start at 0 radians and we go backwards we go backwards pi over 2. We go to negative pi over 2. Here you see at negative pi over 2, that's down there at the bottom, your sine value is negative 1. And at negative pi, negative 180, back around that half, we're at 0. And at negative 3 pi over 2, we're at the top of the circle again, so it's 1. And then at negative 2 pi, I've completed a full rotation backwards, and I'm back to 0. So this pattern extends infinitely in that direction as well. So that's why your domain for theta is all real numbers. Now look at your range for sine of theta. Here your lowest value on all of them is negative 1. Here your highest value on all of them is positive 1. So when we say domain, we really mean the domain of theta, which is all real numbers. And when we talk about the range, we really want to talk about the values of sine that my thetas can take on. And those are going to be numbers anywhere from negative 1 to 1. Now you know there's other values in between 0 radians and pi over 2 radians. So that's where we get things like at pi over 6, it's half. So here at, say, pi over 6, it's half. Okay? And at pi over 4, it's the square root of 2 over 2. Questions? All right, so let's talk about the amplitude. The amplitude is the quote-unquote absolute value of the height of it. So if you look at it from period to period, okay, from 0 pi to 2 pi, it goes up to a maximum height of 1. It goes down to a minimum value of negative 1. So absolute value-wise, from the center to the height, your amplitude here is 1. Amplitude just tells you how tall it is as an absolute value measurement because it's the distance. Questions on amplitude? What is the leading coefficient on sine theta here? What's up here up front? 1. There's nothing written there, so it's 1. So whatever's up front here, the absolute value of that is going to be your amplitude. So here we're going to start looking at transformations. So the transformation rules that we learned last semester and that we learned in Algebra 2 and that we learned in Algebra 1, they don't change. So if we multiply to the outside, that's your vertical stretch or compression. If we add or subtract on the inside, that's your shift left and right. If we add or subtract to the outside, that's your shift up and down. So we're going to look at how that looks like on the sine curve itself. Today we're just going to look at vertical stretches and vertical compressions. All right, this is the last time we have to find this. Your period is 2 pi, so we split that into 4. And again, we're going to measure in pi over 2s. As long as you remember that sine and cosine go by pi over 2s, you're good to go. So again, we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. All right, so now let's see what happens when we plug those thetas in for sine. So what is the sine of 0? 0 multiplied by 3, still 0. What's the sine of pi over 2? 1. What's 1 times 3? 3. The sine of pi is 0, so 3 times the sine of pi is 0. The sine of 3 pi over 2 is negative 1, so 3 times the sine of 3 pi over 2 is negative 3. And then 2 pi again wraps us around to 0. So what I'm going to do first is I'm going to graph plain old y equals sine theta. Okay? This is what we just graphed on the previous screen. Because I want you to see the relationship with this vertical stretch, what that does for us. Mm-hmm. So there's plain old y equals sine theta. Quick sketch that in. Now we're going to graph our actual problem here, y equals 3 sine theta. So again, we have that 0, 0. Except now at pi over 2, I'm going to stretch all the way up 1, 2, 3 units. We still have pi 0. At 3 pi over 2, I'm going to stretch 1, 2, 3 units. And we're back to 0. Again, that pattern continues here. Yeah. For your homework tonight, the book says just to go from 0 to 2 pi, just to do this half of the graph. But for your homework, I want you guys to do from negative 2 pi to positive 2 pi, because I want you guys to see the whole pattern. Okay? So you can kind of see how we have this vertical stretch of 3. I've grabbed the mountain and the valley, and I've stretched them apart from each other. So now here, how would I define my amplitude? Your amplitude is 3. Questions on vertical stretches, vertical compressions? All right, so your homework tonight is going to be page 554, numbers 2 through 6 even, except again, instead of going from 0 to 2 pi, I want you guys to stretch your graph from negative 2 pi to positive 2 pi. Okay, questions on the homework? Again, we're only looking at vertical stretches and compressions this weekend. All right, real quick, I want to show you guys a really quick video. Now, this video is from an iTunes series called An Alternative to Pre-Calculus, and you can find it on iTunes U. It's a really good video series that really kind of reinforces some of the things that I talk about in here. So today I want to look at kind of a real-life situation with these sinusoidal waves. Please don't pack up. Please just pay attention. Here we go.
Consider this image that's supposed to represent a Ferris wheel, and this is a bucket on the Ferris wheel or a seat in the Ferris wheel going around. And so we can animate this showing the passage of time. So here the bucket is going around. Now let's say that we were interested, and it goes around for 2 revolutions. Let's say we were interested in what is the height of the seat on the Ferris wheel over time. So let's go back to the beginning. If we want to focus just on the height, what we can do is walk around the Ferris wheel so that we're looking at it as if the people are coming at us instead of the side view of the people, where you often stand if you're looking at somebody on a Ferris wheel. So I'm going to leave it right about there, not dead on, but almost. Now what you see is the seat on the Ferris wheel just goes up and down and up and down. So all that we know is that it's gone up and down. If we want to know about the height of the seat on the Ferris wheel over time, what we need to do is, like we do again on a seismograph, is have a tracer and the paper moves to the left. So I'm going to do that, and now let's animate this. And that generates a sine wave. So very often in real life, things are going up and down and up and down. And we mathematicians think of them as a sine wave, but what's really happening is something is moving rectilinearly up and down, like waves in the ocean, for instance, or the head of a drum going up and down. And mathematicians then say over time, if you want the position of that object over time, it forms this curve, where this is time, and then this is the height. So, trying to bring in the idea of sine and cosine of angles that are a multiple of 0, 90, 180, 270, 360. If we go back to the beginning, then what we can see is that so if this is the sine curve here, where this would be the sinusoidal axis and this is 1, this rotation here represents the sine of 90 degrees equals 1. You see, there's where we are there. And the sine of 180 is 0, the sine of 270 is -1, the sine of 360 is 0, and then we can continue if we want second time around the circle. Hopefully that'll give you an appreciation for where many real-world applications of sinusoidal waves come from, things that are moving rectilinearly, but if we trace it over time, then it makes a sine curve.
Okay, so it's a really good series, and I really like this series. The other thing I wanted to show you is the Khan Academy website. If you haven't been on there, if you go up here to the watch portion, you're going to go to Math, you're going to go to Trigonometry and Pre-Calculus, and then you're going to find Basic Trigonometry, because that's where we are right now. So as we scroll down, you see the unit circle definitions, graphs of trig functions. So here's where we are right now, is graphs of trig functions. So this first video here really kind of reiterates what we did in class today. And then down here you also see some really good videos, I've already watched them, of more definitions for and examples of amplitude and period. So I really recommend that you guys check those out as well.